Hello, welcome. Welcome to Perimeter Institute. Welcome to Perimeter's public lecture series, here live from the Mike Lazaridis Theater of Ideas. My name is Greg Dick. I'm the Director of Educational Outreach, and it is my pleasure to introduce to you a very special guest speaker today. But before we do, a few things. First of all, those of you watching online, Dr. Damien Pope will be live with a team of PI researchers behind their keyboards on the Facebook and Twitter feeds. Use hashtag PI Live if you want to engage in conversation throughout the lecture and if you want to send questions in at the very, very end. And now it is my pleasure to introduce a very special guest speaker, a good friend and Perimeter's own Dr. Roger Melko. Dr. Melko is an associate faculty member here at Perimeter, and he's a professor at the University of Waterloo. But interestingly, he was thinking about quantum mechanics when he was just a boy. When he was hunting muskrats with his father, he was thinking about superposition and Schrodinger's cat. If you want to hear more about that, you can either ask him in the Q&A or there's a little story on Inside the Perimeter. Also, Dr. Melko, he attended University of Waterloo for his bachelor's, followed by a master's and a PhD from the University of California, Santa Barbara. He became the Canada Research Chair in Computational Quantum Many-Body Physics in 2013 and was awarded the Canadian Association of Physicists Hertzberg Prize, Hertzberg Medal in 2016. His research examines the interplay of large-scale computer simulations, quantum mechanics, and other complex problems in physics. Tonight, Dr. Melko will explore the application of machine learning and artificial intelligence to the questions of fundamental physics. Ladies and gentlemen, please welcome Dr. Roger Melko.
Hi, buddy. Thank you. Thank you, Greg. Thank you. Thank you very much. I couldn't have said it better myself. Thank you. Welcome, everyone, to this public lecture. And a special welcome to two young gentlemen in the second row here. My grandfather's in-law, Harry Woolner and Charlie Ernst. Okay. Here's Harry and Charlie during World War II, dressed up in their service uniforms when they served their country, Canada. Harry and Charlie with his lovely wife, Rhoda. Charlie in particular, you'll see, is in his Navy uniform. So Charlie served in the Merchant Marines. So the Merchant Marines were part of the Canadian, merchant navy that sailed in convoys like this. Okay, these convoys. This one's pictured off the coast of Halifax. These convoys were instrumental in delivering supplies to England, to Europe. They traveled in big packs like this for safety. Okay, and Charlie himself sailed on one of these boats, picked up fuel oil down in Aruba, and that oil went over to England for the war effort. Okay. So this is very dangerous work, as you can imagine, in World War II. The convoys were hunted. They were hunted by the submarines of the German Navy, the U-boats. U-boats are famous. And U-boats would shadow the convoys, waiting for ships to drop out. Charlie will tell you some stories that'll raise your hair about falling out of convoy. The rule in the convoys is you never sacrifice a convoy for a single ship, and you never sacrifice a ship for a single man. The reason these U-boats were so deadly that they would pick ships that fell out of convoys, and then they would attack. And they would often attack in packs, sinking these boats. And the consequences were dire. The convoys were deathly afraid of the German U-boats. But the U-boats were effective. They were effective for many reasons, but one of the most important reasons was communication. So the U-boats could shadow convoys, they could shadow individual ships, and they could radio, what they saw going on, maybe the coordinates of a ship that was either in convoy or going to fall out of convoy. And they did this across sort of the vast distances of the Atlantic theater. Radioing their bases, other U-boats, other members of the Navy, and so on. So one of the main reasons that they could effectively communicate across these vast distances, they did with radio frequency. They had radios at the time. But of course, any ally could listen in to what the Germans were saying And if you knew German, presumably you could decipher things like where a ship was and so on. And so when these U-boats communicated across these vast distances to their bases and so on, they did so not in plain messages. Okay, this might be a message that a U-boat would want to send. What they did was they encrypted these messages. They encrypted it in a way so that, hopefully anyone eavesdropping, any ally or any commander of the Allied forces wouldn't be able to read this message. And there's many ways to do this. Okay, here's an encrypted message that what I've done is I've shifted each letter by one. A's gone to B, L's gone to M, and so on. So the goal is to make this look random so that an eavesdropper can't decipher the message. But as you know, people are really smart. And in World War II, there were brilliant mathematicians and cryptographers who would read these messages and would instantly take this and decipher it instantly. So the Germans faced this fact that they needed to basically scramble this so that it looked so random, it was so complex, that no human eavesdropper in the Allied forces could basically intercept this and unravel it. And as you probably know, they did so with this machine. It's called the Enigma machine. It's a mechanical device. It looks like a typewriter. You essentially type letters in, and lights light up with different letters. And an Enigma machine was on all the U-boats and also on their bases and so forth. And what it did was it took this message and it made it very complex by routing every letter that you type through a complicated circuit. So this is what the circuit might look like. If I typed a T, that electrical signal will go through the plug board, the so-called front of that machine, the plug board, through all these rotors, back through some very complicated path, and might light up G, for example. If I hit T again, the rotors would turn, and a different letter on the light board would light up. So in this way, somebody in the U-boat would type out a message. It would become encrypted. Somebody would write down what lights, what lamps were lit, send that over the radio, radio signal, and somebody in the German base would have the same machine, type in those letters, and it would decrypt that code. And in this way, this mechanical way, it was very mechanical. It was a circuit that was scrambled. The Germans would take these messages and they would essentially make them so random that no human could ever decipher that. And what does that mean? I mean, no human could look at this, maybe look for patterns, try to see the patterns underlying this, and get the underlying message. How hard would it be, or how hard is it to decrypt these Enigma machines? Well, so the machines themselves, the Allies essentially did a lot of work even before the war, reverse engineering circuits that predated the Enigma machines. There's many famous stories that come out of the war, the Polish teams that did a lot of decrypting and reverse engineering. Heroes of the war, stole machines from the German Navy and Army in order so that they could see how they worked and see how the circuits worked. But what the Allies didn't have, is the code book that tells you how the machines were set every day. So every day these rotors and these plug boards were adjusted. And those are called the settings of the Enigma machine. Okay? And without those settings, without knowing how at the start of the day how to set your machine, the message would stay scrambled. So the Allies were faced with trying to guess the settings every day. Every message that came out, even though they knew how the Enigma looked, they knew how the circuit looked, they had to guess these settings. And how many settings were there on these machines? Well, it depends on the exact model, but somewhere around the number 10 to the 20. So that's all the possible settings, initial settings of the rotors, all the possible initial settings of the plug board. You multiply all those things together, you get this, what is this number? I mean, 10 to the 20. Is it something that we can handle as humans? Well, to get a better handle on this, maybe it's easier to see it written out like this. It's 100 billion billion. So 100 billion billion is the amount of different settings you would have to fool around with on this Enigma machine every day, to decipher the messages. And if that doesn't mean anything to you, like to me, it doesn't mean anything. Think of it like this. It's basically the same as the number of grains of sand on Earth, which is presumably pretty hard to estimate anyway. So anyone that wanted to break the Enigma machine, to break the codes, every day they would have to essentially sift through a pile of sand, as big as the Earth. And of course, that's something it's impossible. Or so the Germans thought, right? So, the situation was really dire. I mean, this was, I guess I would call this at the time, really the complexity frontier of World War II. The idea that you needed somebody to do this kind of impossible task, which was encoded by this machine, was really the bottleneck. The complexity was the bottleneck. And the situation was so dire that, in June 1941, Winston Churchill knew that if they didn't break this Enigma machine, he was warned that, the supply lines to Britain would be cut off. Charlie was set to enter the war in 42, I believe. So the situation was dire. There's many sinkings. So there's many heroes. There's many people who contributed to the breaking of the Enigma code, as we know. There's many, actually, stories, even locally in our life, like Bill Tutt, who was at the University of Waterloo. But the one man that stands out amongst all others is Alan Turing. And so for those of you who watched this famous movie, The Imitation Game, you really get a good idea for what Alan Turing's contribution to the war was. And he and his group cracked that code. They cracked the problem of the Enigma settings. And they did it just in time. They did it in the same month that Winston Churchill got that warning, in June 1941. Right before the war in the Atlantic was about to ramp up. So I won't tell you how the war ends. You can ask Charlie and Harry after the talk here. But undoubtedly, Alan Turing saved a lot of lives. And that's where my story begins today, is with Alan Turing and the other thing that he was thinking about during the war. Okay? How did he crack this code? How did Alan Turing crack the Enigma machine? He basically built another machine that did the task of counting all the grains of sand on Earth, blah, 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 essentially every day. So, of course, the number isn't quite as big as I mentioned. There's patterns in the data. You could whittle down the number of settings. But what Alan Turing did is he knew how to build a machine like this. This is a famous bombe, B-O-M-B-E, that was built in Bletchley Park, between Oxford and Cambridge, that successfully solved the problem of finding the settings in these messages every day. And so the Allies could start listening into the U-boat communications, essentially starting in 41. This is the great-grandfather of your computer, essentially. And by looking at it, it doesn't look anything like your computer. But it was a product of the same, if you will, theoretical ideas that led to all the technology, information technology that we have today. This bomb had many moving parts. Things spun. It was, by today's standards, a very clunky machine. But what Alan Turing was dreaming of was not this specific machine to break the Enigma code. Alan Turing was dreaming of, a general purpose machine that could solve all sorts of different problems. Not just saving lives in the Atlantic, but also general calculations that you might come up with. Even before the war in the late 30s, he was laying down the foundations for what today we would call universal or general purpose computers. So Alan Turing really had a vision for what we see in front of us today. And so things escalated quickly. Again, ask Harry and Charlie about the war. But by the end of the war, John von Neumann, another giant in the field, considered second in intellect only to Einstein by many, like Eugene Wigner and other people. He really understood what Alan Turing was trying to do. The paramedic at the IIS in Princeton at some point. And by 45, John von Neumann was outlining really the architecture that underlies the computers we have today, the so-called stored program computers. Okay. By 46, the year after the war, people were successful in building a general-purpose computer called the ENIAC, Electronic Numerical Integrator and Calculator. The thing didn't have moving parts. Not like the bomb, like the Turing bomb. It basically used light bulbs, vacuum tubes, light bulbs that turned the logical circuits on and off and rerouted the electricity and so on. So you can imagine building a computer with light bulbs. The thing's burnt out constantly. 46, by 48, Bell Labs had understood how to replace the light bulb. They had invented what's known as the transistor, what we all use today in our computers. And it's almost, this thing's maybe the size of your fist or a bit smaller. It's almost amazing that the transistor, okay, the basic unit of logic, that is like an on or off switch, it's like a signal amplifier, was invented the same year that Claude Shannon, again another giant on whose shoulder we stand, identified that on and off signal is really the fundamental unit of information that can underlie all the computing architecture that we have today. So we call it the bit now. It's a 0 or 1, it's an on or off in the transistor. 48, think of that. By 51, essentially there was mainframes being produced, general purpose mainframe computers that were being produced and being used, in this case, I think by the US Census Bureau. The Universal Automatic Computer, I think was what the UNIVAC stand for. It actually successfully predicted the 1951-1952 election. It predicted that Eisenhower will win. So, computers are already involved in the US elections way back then. So it's fascinating. A big problem with these machines were that these transistors were wired up with wires, and that problem, resulted in big bulky cases full of wires. That was solved only in 58. In 1958, Texas Instruments invented the so-called integrated circuit. So it's by putting the transistor on board with on the same wafer, the same substrate as all of the capacitors and all the circuit elements and everything else. They invented the technology that allowed us to start shrinking these machines. Okay, in 58, 61, IBM, International Business Machines, right, was patenting business machines. The 1400 was their sort of most famous mainframe at the time. It was the first to replace vacuum tubes with transistors that initially were wired up with wires and later became integrated with the circuitry. 61, 64, this is what mainframes looked like back then. In 64, the world's best machine, the CDC 6600, could perform 3 million instructions per second. 3 megaflops for the aficionados in the audience. And I don't know what happened in the late 60s, but then people really started imagining what the future was going to look like. And Star Trek, as we all know, really sparked our imagination in terms of, the future of computers, handheld devices, tricorders, communicators, translation machines that we could talk to aliens with, I don't know. Yeah. And from there was no stopping it, okay? Think about where you fall in on this timeline. What's the first computer you held in your hand? Like a calculator. HP 35, this is the first sort of handheld, solid state, integrated calculating machine. Only 77, Apple II, the year I was born, 1977, this came out. It's amazing, right? Commodore 64, many people had these. This is my first computer, TRS-80. Radio Shack, color computer. You save the programs on a tape drive, you had to plug it into your TV. I learned to program BASIC on this. TRS-80, that was 83. This is probably most of your first computers, an NES, or any gaming computer, an Atari, for example. Remember 286, 386, 486, 586 was the Pentium. I mean, these advances were coming in rapid fire by the 90s, right? And then by 96, we had flip phones. We almost were living in Star Trek. Of course, the BlackBerry, the reason we're all here, the BlackBerry is important because it integrated us with essentially the internet, right? I mean, we're all nowadays much more integrated than even back then with the internet, with our, we think of it as our email, but that's evolving. I'll talk a lot about that. The iPhone changed everything in 2007. And I could keep going, but the point is, since World War II, technology has rapidly sort of advanced. And we're living in days now where we can fit, and by we I mean the sort of industrial memory of Intel can fit 100 million transistors per square millimeter. 100 million. So each transistor now that's being manufactured in these big semiconductor fabs is something like 10 nanometer. 10 nanometers is how much your fingernail grows a second. So it's like every single one of those transistors is that size, and they're packed onto this chip here. So enter 2018, and me, what am I doing, right? Why do I care? So I'm one of the biggest users of computer calculational power in the country. I use this machine over at the University of Waterloo called Graham. It's a big sort of a shared user machine with 35,000 CPUs, so 35,000 of each one of those machines out of 10 nanometer transistors, essentially. Okay, the thing's huge. It weighs 20 tons, they say. I don't know. It seems massive. It's as big as those mainframes, but it's much, much more powerful. You know, the sort of complexity of that machine is really powerful. It can store 10 to the 17 bits of information, zeros or ones, of this fundamental unit that Claude Shannon taught us. So it can almost store as many bits as there are grains of sand on Earth. You know, it's 1,000 times less. But it's getting pretty close. These are incredibly complex machines. And so why do I need this? You know, what am I doing that requires this kind of massive CPU power? So what we do in University of Waterloo and here at Perimeter is we study the properties of quantum mechanics and the way that quantum mechanics manifests itself in the macroscopic scale. So for example, in things like superconductors, which levitate in a magnetic field, a type of material that's quantum mechanical in nature has to be cooled to very, very low. These things may be 70 or 80 degrees below zero. Quantum mechanical effects get manifest on the macroscopic scale. Quantum fluids, this is superfluid helium. It's being X-rayed in a really sophisticated refrigerator, which has cooled it to probably 2 Kelvin, something like 270 degrees below zero. What's happening here is the quantum mechanical properties of the fluid have become apparent, and it's ceased to have any viscosity, and so it basically fountains out of a straw. It's a really particular behavior of quantum fluids. We study things that you might not think are quantum mechanical, like water. This is a picture from my friend's lab, chemistry lab in University of Waterloo, Pierre and Nicolas Roy. Shout out to Matt Schmitty and Kevin, who made this figure. This is a simulation, a real simulation of the quantum mechanical nature of water, H2O. Each one of those strange paths is sort of the path of, or the projected path of the atoms in space-time or something like that. So these types of quantum chemistry simulations use a massive amount of basically CPU power. And of course, quantum computers, the thing we're all trying to invent. Here's what IBM's quantum computer looks like now. So this is 5 qubits on a chip, coupled with various electronics. And we're still trying to understand these devices and design them. And so that's what we're doing, but why is it so hard? I mean, the underlying issue is that we have many quantum particles, okay? Many particles that we understand maybe the underlying equations, but as we get them together in this many-body system, strange and wonderful things happen. They decohere, they lose their identity. If we perturb the system with a temperature or with some sort of external vibration, these delicate states kind of fall apart, and the thing that we're looking for, the quantum nature, can just evaporate, and it's very difficult to capture this nature on classical computers. So, by the way, that wasn't a real simulation. I was just trying to stimulate your imagination. But when I thought about what quantum mechanics is and why it's so difficult, I was stuck. I thought, how am I going to explain this to an audience? And there's many interesting and wonderful and spooky things about quantum mechanics, but the answer came to me when I was reading this book with my grad students, the ABCs of Physics. And under Q, by Chris Ferry, by the way, I really like this book. Under Q, I found Q is for quantum. So quantum is the smallest unit of energy. So it's very accurate. This is a great book. It's the amount of energy an electron uses to travel from one orbit to another. So if I have a proton and a neutron, there's an electron that can be in various different, let me just call them states, that are signified by those circles. And what quantum mechanics tells us at the most basic level is that the electron can only be in some discrete number of states. So let me boil that down. Let me get rid of the book. So here's a proton, a neutron, and an electron. What quantum mechanics says is that there's various levels, maybe energy levels, that the electron can inhabit. And it can only be in, say, this one or this one at very low temperatures, but nothing in between. So the idea of quantum mechanics is there's some excluded space, or there's some unit, a quanta that it's called. And so let's think about the many-body quantum problem through this lens. Okay, so let me take my electron with two states, my atom with two states for the electron. Okay, and let me ask, what happens if I have, a quantum atom or molecule or material that has, say, two atoms in it, okay? Each one of those states can have, each one of the electron can have two states, so close or far. And 2 for the left and 2 for the right means 2 times 2 is 4. So there's 4 total possible states that a two-atom system can take. Okay, so that multiplication is important. 2 atoms isn't very big. If I have 3 atoms, okay, then 2 times 2 times 2, 2 to the 3, I get 8 different states. So from this kind of exponential counting, we immediately see what's difficult with quantum mechanics in a many-body setting, and that the number of atoms goes right up here. It goes in the exponent. So things escalate quickly. Here's a strange number. If I have 268 atoms sitting around, the number of states of that, molecule or nano-sized piece of dust or whatever it is 2 to the 268, or that's equivalent in base 10 to 10 to the 80. Why did I pick 268? I don't know. No, I do know. It's the number of particles in the entire universe. 10 to the 80 is, if you count all electrons, all protons, all neutrons, everywhere. This planet, all planets, all stars, all nebula, if that's a word. All the particles in the universe amount to the number 10 to the 80. So imagine that. If I want to encode or store or search through the state space, the different types of states possible in a 268 atomic system, which is very small, it's equivalent to the problem of counting all the particles in the universe. It's like the Enigma machine, but way, way worse. So this is the complexity frontier right now. This is what stops us, in some sense, from fully understanding or appreciating the quantum many-body problem, the problem of many quantum particles. And so now you're asking, okay, well, what are they paying me for, basically, right? This looks impossible. And even with the world's best computer, it seems to be impossible, because I'm never going to make a computer hard drive that contains all the particles in the universe, because then what will we make you out of? What will be left? So clearly there's problems that computers will never solve. You'll never, ever solve a problem of that complexity, right, in that sense. And you already knew this, right? That's the point. I mean, I just gave you a mathematical argument for some sort of physics or mathematical understanding of the universe. But we already know that there's other problems that computers are terrible at. Writing poetry. You're never gonna have a computer recreate this poetic, being creative, all these human type things, right? There's a lot of creativity that goes in putting a urinal in an art gallery. I saw it. I mean, only a human could do that. Painting, Rembrandt painting all these weird old people. I mean, can a computer do that? Of course not, right? Even something simple like a tree. There's a beautiful Rembrandt, a picture of a tree. So, why not? Why can't a computer paint a tree? I mean, or if I wanted to construct a computer program and an algorithm to paint a tree, I guess at first I would have to tell a computer what a tree is. So let's ask the question: how would I get a computer to understand what a tree is? Okay, that's a simpler question. Here's a simpler tree. It's black and white picture of a tree, a photo, if you will, and I want to design an algorithm so that if I feed that image into a computer, I can identify that as a tree. Okay? So let's make it simpler. Let me pixelate it. It's a pixelated tree. There's maybe, a couple hundred, maybe a couple thousand black and white pixels. Okay? And let me imagine I have a computer program where I feed in those pixels, and I ask the computer, is this a tree? And the computer says, well, okay, I'm looking for a trunk in the middle, maybe some branches on the side. I guess there should be nothing around the edges and maybe some ground in the front, but that doesn't matter. It's still basically a tree. And so I can imagine, okay, I'm going to code in the XY coordinates and blah, 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 and try to make up a deterministic program to And then, somebody says, oh, what about this? Is this a tree? Well, yes, but now I got to think about, okay, I need to have the trunk kind of going horizontal in some cases. And quickly what you see is that the complexity of making a deterministic algorithm to take in these pixels and tell you that that's a tree is difficult. And how difficult? I mean, you can ask that question. Well, pixel space can be counted. Now, here's a pixel, black and white. It has 2 states, right? So 2 states per pixel. If I have 2 pixels, it's 2 times 2 is 4 states of those pixels. So an image, there's 4 possible images that I can make of 4 pixels, and you see where I'm going. If I have 3 pixels, there's 8 possible images that I can make out of those. And I can, again, 268 pixels, it's not a very high resolution photo. You're essentially never going to be able to search all of that pixel space or all of that picture space. So the state space, if you will, is similar to quantum mechanics. But let me get back to that. Because I know that I can make a computer identify a picture of a tree. So I uploaded this picture from Killarney that I took of a tree for some reason into Amazon Web Services. So Amazon online has basically a free program. You can all sign up for it, and you can shoot all your pictures into Amazon Web Services. And it has a feature called something like image interpretation, where it attempts to tell me what's in this picture. And here's the results. On the left is the object that it believes is in the picture, and on the right is the confidence that it has. And Amazon Web Services is 96.3% confident that this is a conifer, and I had to look that up, so it's already doing better than me. I didn't know what a conifer was. But luckily down here there was tree. And so Amazon Web Services told me that there's a tree in this picture. It's exactly the thing that I just told you was difficult, or it's kind of astronomically impossible or astronomically complex. It knows there's a forest land. I love it, vegetation, pine, bush, landscape. This thing's really amazing. So I got addicted. I started uploading all my photos. What is this? Aircraft, 98.8%. Vessel, a dinghy. That's pretty accurate. 73% that chance that this is a dock, not a pile of sticks. It was very great. Is my dog being bad? It's 91% sure that this is a golden retriever. It's better. It is a golden retriever. It knows it's not there's a lot going on in this photo. And Amazon Web Services is very good at telling exactly what the objects are in this photo. Here's me winning the cup with the boys up at Gravenhurst. Knows we're human, that's great. Knows not so sure about hockey, but we have no sticks, so I understand that. But what happened here, which freaked me out, was you turn a little switch on Amazon Web Services, and all of a sudden it starts to identify faces. It knows where the faces are in the image. Okay, 99.9% sure that that's my face. It thinks I'm 48 at minimum. I've lived a hard life, but I don't. No. Mouth is open. It has a beard. It's pretty accurate on most things. Then I got addicted to this. I was uploading all my photos. Here's my lovely wife. 100% sure you're female. Thank God. It thinks you're 26. That's amazing. I love Amazon now. You're not going to identify any face. 91% sure Trump's smiling, but only 69% sure that he's happy. This is scary stuff. Amazon recognition, this is called. Try it. This is what Amazon says about what's going on here. This is based on the same proven, highly scalable deep learning technology developed by Amazon's computer vision scientists. Okay? So deep learning, keep that in mind. Computer vision scientists that analyze billions of images and videos daily. Process that. Billions of images and videos are flowing through Amazon servers. And somehow it's processing so that it can learn what a tree is and what a golden retriever is and all this stuff. So what's going on? So this is something very new in the world of computer science. It's a new breed of algorithm. Artificial intelligence, that's what we call it. Artificial intelligence is kind of a catch-all term for many different types of ideas related to smart machines, if you will. A subset of these ideas are the types of machine learning algorithms that we actually work a lot on at Perimeter here. And a subset of these I'm going to talk about, these algorithms are called neural networks. And what you just heard about from Amazon was deep learning, which is a subset of neural networks, so deep neural networks. So this new breed of algorithm does tasks that seem impossible for computers, but are possible for human minds, like adult human minds. Okay? It's very new, but it's actually not that new, the idea. If you go back to Turing's writings during the war, before the war, and even especially after the war, he could envision exactly what's happening today with artificial intelligence, even looking at the sort of rudimentary hardware that we had back in World War II. So he was saying, if you want to have a computer that simulates an adult mind, essentially you should build a computer that's like a child's mind, and you should take that child's mind and teach it, expose it to data, educate it. That was Turing's vision of artificial intelligence. And, it took years for us to realize that vision, but the revolution we're seeing now in Amazon Web Services and all over in Canada and other places is because of this vision. So what does this mean? Educate a computer and obtain the adult brain. Well, these algorithms, these deep neural networks, are called that for a reason. They're essentially motivated or designed based on principles that we see in human and animal brains. Okay, so the idea that there's pathways and that pathways have sensory input, which strengthens them and which leads to some sort of thought process and so on. This is really motivated by the way we process data ourselves. Okay, hence the name, neural networks, and so on. So the workhorse of most of the machine learning breakthroughs that have happened recently is this object, an artificial neural network. So an artificial neural network is like a small piece of that human brain encoded in the computer to learn based on experience. And how it works is you can imagine on the right-hand side, like the pixels of an image, maybe it's your retina, maybe it's your eye. And as you go further back in the network, there's neurons and pathways, and the pathways take signals and the neurons let them pass, or maybe it stops them, or maybe amplifies them, such that you can train this thing, or you can educate this thing. So the way it's done in Amazon and most other places, you take a whole bunch of images, billions of images a day, and you might have somebody tell that network for each one of those images whether or not the person in the image is happy or sad. So you yourself don't have to program that computer. What the neural network's doing is strengthening pathways that take you from that pixelated image space to the output that you want. The last neurons will fire happy or sad based on that pathway. So then you can take an image that it hasn't seen before, like a happy Trump, and you could put it in the neural network, and if everything goes well in the training or the education, the neural network will fire the neuron that tells you that that's a happy face. And that's what's going on in Amazon. It has many of these neural networks trained on tons of images. If you take that same neural network and feed it in a sad picture of Trump, then it'll hopefully fire the pathway that tells you that there's a sad picture coming into it, right? So the idea of neural networks is sort of the same philosophy as learning. But what I just showed you is that image space, these pixelated images are very similar in many ways to the state space of quantum mechanics. Okay, so actually the size of image space is identical to the size of state space in quantum mechanics. Even though quantum mechanics is more highly complicated. Let me just say complicated. So this made me wonder, can we take neural networks that understand images and replace those images with images of the quantum state? And what are these images? Well, my group and my friends who do computational quantum physics, we do this for a living. We produce very complicated images. So here's an image from my friend Adrian Del Maestro in Vermont of us producing an image inside of those massive computers that I showed you. This is 12 or 13 helium particles, which are basically propagating through space-time, forming these long chains. Okay, this is like their quantum evolution in space-time. We've done something to wrap these around in a periodic way so that they appear on a torus on the right. And those individual particles have different states. The blue states might be normal, fluid states or something like that, and the pink states might be these quantum mechanical superfluid states. So from this type of simulation, I can produce basically raw images of what I imagine quantum states to look like. These might be difficult to process, and they are. And what we do now is we train neural networks. We just take that raw, unprocessed data, and we feed it into neural networks. And then if the neural network sees enough data, we can ask it, is that a superfluid? Is that a normal fluid? Right? Something like that. This works. This proof of principle works, and now we're adapting this to all sorts of data that lives in the quantum domain. Data from simulations, like we produce in our group here, which is this is a phase of a wave function, to the middle, which is an actual microscope image of a gas, a gas near 0 Kelvin. Each individual green pixel is an individual atom. So these are atomic resolved gas microscopes, basically. On the far right is atomic resolution in a superconductor, essentially a solid-state ceramic cooled to very low temperatures. And we can process these, we can train these massive neural networks to analyze these images essentially automatically. Anyway, I don't want to talk about that today. Have you ever thought about what would happen if you ran this thing backwards? So you asked it something, hey, can you produce me an image of a tree? And what pops out? Would a tree? I don't know. That's what I thought. So you can do this. You can take the same neural networks that have been trained and essentially run them backwards and produce images. And here's some cool examples of what I thought was impossible. Neural networks painting trees. We've taught the neural network what a tree is, and then we've asked it what it thinks a tree is, and this is what it tells us. This is the interpretation of a tree coming from deep inside the latent space of a neural network. It's almost, looks, I couldn't tell the difference between this and a Rembrandt. There's no way. You can also do crazy things like ask these deep neural networks what they think humans look like. And this is what they spit out, which is, I don't know if this is good or bad. You can do all sorts of things with this. By the way, this is a famous artist who does these paintings with artificial intelligence. No Picasso or Rembrandt. His name is @DrBeef_. So I encourage you to follow him on Twitter. He's got a lot of these sort of neural network inspired images. This process of producing these crazy images is called deep dreaming. You're asking the neural network to dream what it thinks something looks like, or what it thinks something in this pixel space should look like. And it's also called hallucinating. And if you stare at these things too long, you'll start to realize why. Some of these really are nightmarish hallucinations, and this is really what the artificial intelligence is thinking. Here's this is some transfer learned deep style generator. You've trained it on Van Gogh and then fed it pictures of pufferfish or something like that. Trained it on dogs and fed it a picture of spaghetti. So these things are easy to fool. I'm not hungry anymore either. We can do the same thing with our quantum data. So we can take all of this data that I showed you, either produced on a computer or produced in an experiment, and we can feed it into neural networks. And the data looks like stuff like this that we're doing on the machines, or stuff that's coming out of the labs here at IQC. So this is something we're doing over the summer, is we're taking these big, complex experimental setups, like in Kevin Resch's lab, and we're hopefully training neural networks on the data that's produced in these expensive experiments, and then using that data to train neural networks and hallucinate states, right? And the amazing thing about this is that like I said, these states can be very expensive to produce. We have the biggest computers, we have the most expensive laboratories, but once I train a neural network on this data, anything can come out. I mean, I can, in principle, hallucinate states, if you will, that are states that have never before seen in any experiment or any simulation. I can take these hallucinated states and I can ask about their properties. I can ask, is this phase structure something that I want to build in a quantum computer, or does this somehow help me solve high-temperature superconductivity? The amount of kind of possibilities, I think, are endless for these hallucinated states. But, okay, that's what we're doing now. Where are we going? What's going on with artificial intelligence? We are entering a realm of sort of technology that we can basically only return to science fiction to sort of tell us what to expect. And I'm not in the business of predicting things, so I don't know what the future will bring us. But some things will definitely be great, like a universal translator. This is almost reality. In 2016, Google changed its translation services from the old system, which I won't mention, to a neural machine translation system, which basically takes phrases in different languages and trains these massive deep neural networks. As shown in this plot, the neural machine translation systems, by some arbitrary count, seem to be almost as good as humans. At translating. So what's going to happen in the very near future is like an earbud in your ear, and somebody speaks in French, and I no longer have to go to French class. My phone will translate that in real time. Great. It's what I always wanted. So that's one thing you can look forward to. For every good thing in the future, there's also things like this. Facial recognition technology that can now text you a fine as you're jaywalking across the street. This isn't the future. This is happening now. This is today's technology. Okay, so you got to, I guess, wonder what kind of future you want to live in. You know what I love about this? This red eye. Where have you seen this before? I know where I've seen it before. It's like whoever wrote that article was thinking of Skynet. And we should all be thinking of Skynet. Are we creating, human-like intelligence? Do we want to create human-like intelligence? Are we capable of it? What would artificial intelligence look like? I get asked this question quite a bit. So in terms of human-like artificial intelligence, creating a brain out of these artificial neural networks, I think we're a long ways from this. The only kind of intelligence we know is our own, and our own brains are very complex. They have the same amount of neurons as there are stars in the Milky Way galaxy. Okay, that's a big number. That's 100 billion. That's the number that quantifies the complexity of your brain. We're nowhere near making artificial neural networks that have this type of capacity. This type of neurons and this type of connections and so on. The brain's a fabulously complex device. But what we are very close to is augmenting our current reality and our intelligence with the very technology that we're basically creating now. Okay? You already live in an augmented reality when you listen to headphones and the music's superimposed on your everyday experience. Virtual reality is kind of the limit of how you would completely immerse yourself. But really, the idea of augmenting your day-to-day life with a watch that sends you your emails, I don't know why you'd want that. I hate it. My Apple Watch lasts about 3 days on my wrist, but that device is augmenting your reality. It's telling you the weather, it's telling you your emails, your texts, and in turn, you're feeding data up into the big neural networks that live on the cloud. It's a very symbiotic type relationship. The thing with the human-level intelligence, like building a brain that's the size of our brain and as complex as our brain, is you really have to teach it things, just like Turing told us. You have to expose it to experiences, and you have to structure that data in a way that enables it to learn. And the best way to do that is with devices like this, these Amazon and Google Home speakers that are constantly on, constantly listening to you. They're very convenient. You can ask things of them. But the trade-off is that your data is constantly being used, just like it's used in Amazon Web Services, to train these neural networks, with billions and billions of natural language texts, sentences a day or something like that. So we can augment our reality and our intelligence, and one question is, how far do we let that go? Are we willing, for example, to get rid of our iPhone screens, shrink the size of the device down, and just project the image directly into our eye? What I'm showing you now isn't the future. These are real companies. Okay, look up Verily. These are patents filed. These are startup companies that are in the process of essentially integrating your phone with your body. So smart lenses is a nice first step. Put contact lenses in, heads-up display, Finally, when I'm meeting my grad students, their name comes on the bottom. I know who they are. I could really use that kind of augmented reality. There's technical problems only with this type of smart lens. Some people are putting their money more on retinal projection. Okay, Intel Vaunt was a prototype retinal projection system where you might wear glasses, but instead of having a screen, you essentially project your iPhone screen or whatever directly on the back of your retinas. So now it's starting to be a little creepy, right? How much do I really want beamed directly into my brain? Well, you can ask the other question, how do I change the way that I interact with the phone? I mean, this is the phone feeding me data. How do I want to interact with my phone? Isn't it annoying when you have to reach up here to turn your headphones up and down, right? Don't you wish that you could do that with your mind, just thinking about it? That's crazy, right? Brain-phone interfaces, the idea that we move ahead by letting our phones literally know what we think. Just think it. It's a nice logo. Actually, this is a real company, Orbital Labs. Orbital Labs, who I met in Toronto recently, is a startup company building the world's first earbuds that let you control things with your mind. And they're going to start with the volume on your phone. You're walking down the street, you want your phone, your music at a higher volume. You can basically think it. The EEG pattern, produced by your brain, can be interpreted by these earbuds to essentially give instructions to your phone. And the easiest instruction is the binary instruction, up or down. Okay? That's a real company. This is, again, not the future. And you know what else is not the future? Getting rid of that pesky skull on your mind, that surrounds your mind, that interferes with those EEG signals. Because wouldn't it be much more, energy efficient to get those EEG signals directly from your brain? So, no, I'm not kidding. There's syringe injectable electronics being developed. This is a paper out of Harvard with plug-and-play input-output interfaces. So the idea is that you syringe inject basically a sort of electronic wiring into your brain, which enables these types of interfaces to happen. And big breakthroughs have been achieved in injectable electronics that don't provoke some sort of immune response. So they're not. That was the big holy grail, not rejecting these brain implants. I don't know. How do you feel about that? These are where technologies are going. Again, it's accessing massive amounts of data. It's taking all this big data that you're producing every day and training these massive neural networks. Okay, it's interfacing yourself with the phone in a much more sort of fluid way, so that this data transfer back and forth really helps you augment reality without all these pesky things like typing on a keyboard, turning your headphones up and down. I don't know what you guys think about it, but I'm pretty excited about what this technology means for my type of research. All of these pesky quantum particles that I had a hell of a time, I guess, characterizing and understanding. Now what we're doing is we're essentially interfacing these neural networks directly into either the data produced in our computers or the real experimental big data that's being produced in measurements of these wave functions. And these neural networks, coupling with our sort of quantum data, are really augmenting that data in such a way that I can understand it myself. When I look at my computer screen, when I look at the processing that comes out of our scripts, I've really seen that neural networks have augmented the reality that is quantum mechanics. As we move forward into the future and we build the next type of intelligent machines, which are quantum mechanical, quantum computers, we will also control those machines, we'll interface with those machines, we'll do readouts, we'll nurture them, we'll train them, we'll give input. All of that will be done through artificial intelligence. It'll all be done through these types of neural networks that we're developing today. So we're really on the verge of actually doing this experimentally, and we're really taking our next generation of quantum intelligence and augmenting it with our most advanced artificial intelligence that we have today. So I can't predict the future, like I say. I don't really know where this is going. I'm very excited, and what it means to me is that we've taken what I thought the frontier was, the sort of complexity frontier of quantum mechanics, and we've pushed it to some other level that we don't even fully understand yet. So that's my vision of the complexity frontier. Harry and Charlie, thank you for coming. Everybody, thank you for your attention.
So let's take some questions. We'll open the microphone. It's right here, and also online. You can send your questions in. But I'm going to start with, what made you start chasing quantum in the first place? It doesn't have to be the Muskrat story.
That's a tough question. I come from a field called condensed matter physics, where we basically try to understand quantum materials. And I think what I realized in my PhD was that the problems of understanding quantum materials were converging on the problems of studying quantum computers. And so really it came from, for us it was a materials perspective, is the idea that we're designing new materials. We're stuck on certain problems, but these problems are the same problems that we're stuck on when we build quantum computers. And so that really kind of piqued my interest, I think, in this whole quantum information world that we see today.
Good. All right, online I have a question from Ethan Siegel. It's a little bit long. Right now, most of what AI machine learning can discover is based on how successfully the algorithms are programmed. Could a machine devise a force law on its own? Could it have come up with relativity or Schrodinger's equation? And if not, could it do so in the future?
I get this question a lot in physics audiences. One thing I'd point out is that our sort of modern edifice of physics is based on seeing patterns in data. So when Brahe wrote down all of the positions of the planets as a function of time on these big pieces of paper, and Kepler came and looked through those. He used his human mind and he looked through those and discovered Kepler's laws of planetary motion, and these laws led us to Newton and Newton's equations and F equals ma. The same thing happened in quantum mechanics. People saw the Balmer series of hydrogen. They noticed that there were certain energy levels of those atoms, and they knew the structure of those energy levels in data, and that spurred them to think about theories that would give you that data back, essentially. So humans develop physics through pattern matching. What we've done now is we've developed a suite of algorithms that are as good as humans, or better in some cases, at pattern matching in data. So the future is wide open for those machines.
In the theater.
Okay, my name is Bovis Abraham from University of Waterloo. Any tool in the hands of a destructive person can be dangerous. Now, we have seen technology in the hands of people who want to manipulate things. Now, in this future kind of thing that you were envisioning, getting in the hands of somebody, we are seeing hacking all over the world. What is your thoughts on that kind of a tool in the hands of people like that?
Yeah, it's a good question. I mean, we should all be asking that. It's the same as when you talk about nuclear fission, right? You can't put that genie back in a bottle, ever, as far as we know. So we can't put the AI genie back in the AI bottle now. I mean, Putin himself has said that, to paraphrase, he who controls AI will control the world. And you can already see this in terms of things like the elections that are coming up. One thing that really struck me as some of these style transfer algorithms that could take a human voice, like I could say something and superimpose it on a video of another person. So it was done to Obama recently. And so he'll be saying some things in this video, look it up, which of course Obama would never say. But the quality is seamless. Somebody like me kind of hacking together algorithms to identify pictures of dogs, can take the next step pretty easily and take these same algorithms from these online web servers and start to, essentially fake video. And that's the first step. We're going to live in a sort of world of information that's difficult for us to, I think, interpret. So, luckily I stick to peaceful things like quantum mechanics. Yeah.
There's actually a question that then follows along from that. You're using it for quantum mechanics. Do you think it is also in use, or will it be put to use for other questions like the Big Bang?
Yeah, so we're actually late adopters for this technology in my field. Other physicists have used this type of artificial intelligence or neural networks for years. So a famous one is CERN, particle physics. They produce a ton of data. They're colliding atoms and they produce all sorts of byproducts of these things. And they have a big signal to noise problem. There's a lot of cosmic rays flooding through their detectors that they have to kind of subtract off the signal. And the best way that they can do this is with big data processing things like artificial intelligence. So particle physics for years has already used this type of technology. Astrophysics, when you take galaxies and stars and you look at their spectra and you want to classify them and so on, that's also a big data problem in astronomy, and people have used these types of machine learning or artificial intelligence methods for years there.
Ladies and gentlemen, Dr. Roger Melko.
Thank you.